Professor Levine is a member of Academia Europaea and the full member of Leopoldina. It's a German National Academy of Science. He is was also a ICM Invite Speaks in 2002. So let's welcome. We will talk about the Motivic homotopy theorem and the quadratic enumerative geometry. Okay, so let's welcome.
Thank you very much. Is the microphone is on? Very good. See if I can actually start the timer. So yes, thanks for the introduction, and it's been a very stimulating and exciting week of lectures and discussions, and I'm very happy to have been invited here to speak to you. Let's get my pointer. So quadratic enumerative geometry is an attempt to refine classical integer-valued invariants of enumerative problems, such as how many lines are tangent to two conics in the plane, 4, I guess, and to a quadratic form. And the quadratic form is supposed to, on the one hand, recover the integer information by taking the rank of the form. If you're over a field with an order, so for example, the reals, the associated signature is supposed to tell you something about what happens over the reals, over the real embedding corresponding to that order. And then there's additional arithmetic information in quadratic forms, discriminant, Hasse-Witt invariant, other invariants. The more complicated the field is, the more such invariants you have. And those are supposed to tell you something which is at present rather a mystery. So maybe you'll be able to solve the mystery for us. I'm going to start with telling you where these quadratic invariants come from. They have their roots in the Motivic stable homotopy category. Don't be scared about this. It'll soon become quite concrete. But the basic structures in this category enabled, as developed by Morel, Voevodsky, Ayub, Huayhua, Szynski, de Glees, and many others, enabled de Glees, Jin, and Kahn to construct a enumerative geometry or a intersection theory for in a very general setting. So I want to tell you about that because I think it's in itself very interesting and perhaps you can use it yourself. So we have this, B here will be a base scheme. Eventually we'll just come down to B being spec of a field. Don't worry about general scheme so much. You usually assume that B is Noetherian and finite Kroll dimension. But as I said, usually we go down to a spec of a field. And I wrote that schemes over B are finite type separated B schemes, but again, as Burkhardt mentioned, we really can just restrict to quasi-projective B schemes, if you like quasi-projective schemes over a field. So don't be scared by that. See, does this pointer do anything? No, really? Good. Nothing. Does? What's the pointer? Do you see anything? Oh, there it is. Okay, well, it doesn't matter. Okay, so the basic construction associates to one of these B schemes triangulated, so tensor, in other words, symmetric monoidal category, the Motivic stable homotopy category of X. And you can think of this as a sort of refined version of the derived category of, say, sheaves of abelian groups on X. It contains a lot of information about homotopy theory and at the same time about algebraic geometry. That's the idea in the construction. So, and central to these structures, as you vary the B scheme X, is the so-called six-functor formalism. So, of course, for any morphism Y to X, you should have a pullback map, F upper star, just as you do for sheaves. And that's a left adjoint to a F lower star. So I'm sure that's familiar to you. And then you also have these exceptional functors, sort of going, the adjunction is in the opposite direction. The F lower shriek is left adjoint to the F upper shriek, the contravariant one. And you have, so that's 4, and there are 2 more. There's the internal hom and the tensor product or smash product, that's the 6. And there's this extra one, the F lower sharp, which is in some sense the most elementary one. This is the left adjoint to F upper star, but just for smooth maps. So it's really sort of 6.5 functors, if you count properly. And they have the expected properties. The pullback preserves the product. The push forward maps are functorial. The pullback maps are functorial. There's a base change property in Cartesian squares. And you have sort of localization. This thing breaks up into pieces. If you have a closed immersion with an open complement, then you get a distinguished triangle in the triangulated category relating what happens on the open. That's the J lower shriek, J upper shriek, sort of compactly supported cohomology, if you like, pushes forward into the identity on the ambient scheme and pulls back to what happens on the closed subscheme. There's also a nice way, the lower shriek you can think of as compactly supported cohomology, and the lower star is like cohomology, and so that gives you a natural transformation from the F lower shriek to the F lower star, and if F happens to be proper, that's an isomorphism, as you might expect. Okay, that's some formal structures. We're probably never going to see them again, but just so you know. So cohomology, that's what we're after here. In the classical stable homotopy category of spectra, don't be scared by that. It's just a category which represents all reasonable cohomology theories on spaces. So it's really these objects. You have various cohomology. You have singular cohomology. You have topological K-theory. You have complex cobordism. All kinds of cohomology theories. And they're all represented by objects in this one category, the stable homotopy category. And this gives you a way of comparing different cohomology theories as morphisms in the category, building new cohomology theories out of old ones, using the triangulated structure. In any case, how does cohomology arise? You have a suspension functor in the triangulated category, just the translation. And you also have a way of taking a space and getting a spectrum out of it, the so-called infinite suspension spectrum. That's the sigma infinity T plus. And you get the nth E cohomology of T is just the maps in this category of spectra from the infinite suspension of T to the nth suspension of E. So that's how cohomology arises from the category of spectra. And I mentioned the various examples. And the Motivic stable homotopy category is built to do exactly the same thing. Objects represent reasonable cohomology theories on B schemes. And the basic axioms are similar to the axioms in the topological setting, just made algebraic. So there should be a Meyer-Vietoris sequence, but for the so-called Nisnevich topology, so in particular, Zariski topology has Meyer-Vietoris sequence. And you also have replacing sort of the homotopy invariance property, you have a homotopy invariance with respect to the affine line. So in this theory, the affine line with its 0 and 1 plays the role of the interval. So we take our E and we want it to represent a reasonable cohomology theory, so it has to have products on it, so we just assume it has products. You don't need any fancy products. The topologists are always talking about E infinity ring spectra. I have no idea what that is. And you don't need to know either. It's just the naive notion of a product in the category. It should be, a product. It should be commutative, and it should have be associative and have a unit. Very simple. All right, so out of this, I'm not going to tell you how, but it's a purely formal construction. You just use these 6 functors, really, the upper star, the lower star, the upper shriek, the lower shriek, etc. And you can build actually 4 theories, but we're going to concentrate on 2 of them. You have your spectrum and you have E cohomology. But there's an important twist to the story. You can twist the theory by a virtual vector bundle. If you like, a perfect complex on E gives you a V-twisted E cohomology. So that's the data. That's the basic input for us. And it's bi-graded Okay, why is it bigraded? If you're familiar with Tate twists, that's the second grading. The B is the Tate twist, and the A is in some sense the topological shift. You can make this, of course, more precise and formal, but probably if I give you the definition, well, there's sort of the definition, you'll see it in a minute, but that's E-cohomology, and there's a E-Borel-Moore homology, which is sort of a dual of the compactly supported cohomology, just as in topology. And yeah, it's a relative theory. The E-cohomology is an absolute theory for things over B, but the Borel-Moore homology is for a map. You have Borel-Moore homology of Y over X, again in bi-degree AB, and with a twist by a perfect complex on Y. So what's the correspondence? Remember, we had the E-cohomology for a space, and the E-cohomology for a B scheme is based on these suspension operators and by this formula. You just, forgetting the twist by the virtual vector bundle, the bi-degree AB cohomology of X is just the maps in this category on X. You pull back your spectrum to X by the structure map. You take the AB translation of it, and you just map the unit on X into E. And using the adjunction, you can put the upper star on the left as the lower sharp. That's the left map if X is smooth. And you can, in some sense, this means you think of this px lower sharp of the unit on X as like the motive of X for a smooth X, if you're familiar with motives. It's really the object in the category for B that represents the smooth B scheme X. So that's our analog of cohomology. And it has the properties that you'd more or less expect. There's a unit in bi-degree 0, 0 on X. You have cup products. They're sort of bi-additive in the shifts, and they're also additive in the twist. The cohomology acts on Borel-Moore homology by cap products in an expected way. The cohomology is functorial. You have, interestingly, the Borel-Moore homology has proper push-forward maps. Again, this is something you can construct entirely using the six-functor formalism and the adjunction. It's a nice and simple and formal construction, but probably wouldn't help to see it. But that's an important property. You also have a smooth pullback, and there you see you have this twist. You don't get a pullback in Borel-Moore homology the way you do in cohomology. You have to twist the twisting virtual vector bundle by the relative differentials. And in some sense, that's a effect of Poincare duality. The Poincare duality identifies Borel-Moore homology with cohomology, but with the opposite twist by the virtual bundle. And again, you have to add a twist by the relative differentials. You may be familiar with this in étale cohomology, where the cohomology with supports is this of something smooth, Z and some smooth X, is the same as the cohomology of Z, but with a shift in the degrees and a shift in the Tate twist. The Tate twist is showing up in these relative differentials in a suitable way. Okay. Now, once you have this structure, you can build Euler classes for vector bundles. You don't get all the Chern classes that you're used to for things like the Chow ring or K-theory, but you do have something corresponding to the top Euler class. So at the very bottom, you see the formula. The Euler class of V is just the push forward of the unit and then pulled back. The push forward by the zero section on V and then pulled back. And to actually do that, you have to really do this funny sequence. You first identify the 0, 0 cohomology of X where the unit lives by Poincare duality with the relative X over X Borel-Moore homology. There's no twist because the relative differentials of X over X are trivial. Then, since it's Borel-Moore homology and the zero section is proper, you can push forward to the relative Borel-Moore homology of V over X. But again, V is smooth over X, so you get another Poincare duality isomorphism. And the twist is now by the pullback of the vector bundle defining, of the locally free sheaf defining V. This curly V is the sheaf of linear functions on V. And of course, that's just the same as the relative Taylor differentials of V over X. So that's why you get this pullback of this script V. And then you pull back to X, and that's where you end up. So it's really, after Poincare duality, it's really push forward, then pull back, and that's the Euler class. Okay, so let's go back to Earth. We have the Chow groups, which I'm sure many of you are familiar with. Yes, sure. Yes. It's like a topological grading. You'll see in a minute, we're not going to care too much about it. If you take the grading, the bi-grading that's important for us is, well, let's see. If you took étale cohomology H upper A, Tate shift of B, that's the other grading. The A would be the topological grading, the first one. Yeah, you can do both. Yes, exactly. Exactly. So we have our Chow groups. It's you take the free abelian group on the dimension n subvarieties, which you can think of as the free abelian group on the dimension n points of your variety Z, and for some reason I call them x's. And then you mod out by divisors of functions on things of dimension n plus 1. And so that's, if you have some variety of dimension n plus 1, x would be its generic point. K of x is the field of functions, and K of x cross is the group of non-vanishing functions, and you have a divisor map. And that's just the group of dimension n cycles on Z mod rational equivalence. Now, if Z is your x, which is now smooth over K, so now we're taking our base scheme to be spec K. That's our field K. And we just, we can re-index by codimension. So it's a trivial re-indexing. But these Chow groups are represented by an object, by a spectrum in the Motivic stable homotopy over K. One way of representing them is by the so-called Eilenberg-MacLane spectrum of the homotopy module given by Milnor K-theory. So that's a real mouthful. It's, if you're familiar with Milnor K-theory of a field, there's a way of extending, I mean, that's very simple. You just take the abelian group of units on the field, take the tensor algebra on that, and mod out by the Steinberg relation, A times 1 minus A should be trivial. That's the Milnor K-theory of a field. That extends actually to a sheaf on smooth varieties over K. That's this MKM star is that graded sheaf. And out of this graded sheaf, it has a structure that enables you to build a spectrum, an object in this Motivic homotopy category out of it. This comes from a theorem of Morel, which says that there's a, and if you want to get a little abstract, there's a T structure on the triangulated category SH of K, and the heart is identifiable in terms of certain sequences of sheaves. That structure is called a homotopy module. This Milnor K-theory gives you a homotopy module, and the inclusion of homotopy modules, identification of that with the heart of the T structure gives you this Eilenberg-MacLane functor. Anyway, it's an object in the category, and the point is that the cohomology in bi degree 2nn represented by this object is exactly the Chow group of codimension n cycles with its ring structure by intersection theory. The Borel-Moore homology is just the Chow groups of dimension n cycles. And so the product is the product in the cohomology. The cap product is how cycles act on cycles by lowering the dimension. The Euler class, as I mentioned, for a rank R vector bundle, is just the top Chern class. So that should be something familiar to you all. So let me just see. Am I doing on time? All right. So other representable theories, you can represent algebraic K-theory, algebraic cobordism, if you're familiar with that. There's another type of cobordism built out of the special linear group. There's symplectic cobordism. You have Hermitian K-theory, which is the K-theory of quadratic forms. You have Witt theory, which is in some sense a quotient of Hermitian K-theory. And then you have two other theories, which I'm going to tell you about in some detail, Chow-Witt groups and Witt-Schief cohomology. So those are the ones which are important for us for this program of quadratic enumerative geometry. So to say what those are, let me remind you about the Grothendieck-Witt ring of quadratic forms over a field and the Witt ring. I'm going to do a slightly fancy version of quadratic forms over a field with values in a one-dimensional vector space over the field. The reason for that is we want to have a theory of sheaves with values in an invertible sheaf, and the L would be the fiber of the invertible sheaf. So if you don't like it, just think of L as being F, and you just drop it from the notation. In any case, we start out with non-degenerate symmetric F bilinear forms on a finite dimensional F vector space V with values in our one-dimensional F vector space L. Okay, if we take a basis for all these things, that's just symmetric n by n matrices, if n is the dimension of V. And isometry is induced by isomorphism on V. Again, if you're using matrices, it's just the relation symmetric matrix B is equivalent to A transpose, where A is invertible. Change of basis matrix. You have two operations. You have a sum operation, which is sort of the obvious way of adding symmetric bilinear forms in terms of matrices. It's just the block addition of matrices. And you also have a product, which is just induced by tensor product of vector spaces. The tensor product bilinear form on a pair of tensors is just the product of the values of the bilinear forms on the individual components. And that's just represented by the, what do you call it, Kronecker product? Is that right? Kronecker product of matrices. So that gives you a, so you have a monoid structure by direct sum. You have a product by tensor product. That forms a commutative semi-ring, which is an uncomfortable type of gadget. So you make it into a commutative ring by taking the group completion with respect to the direct sum. So elements you can think of as just formal differences of symmetric bilinear forms. Of course, if you have a symmetric bilinear form, B of xy, you can form a quadratic form by just taking B of xx. And if the characteristic of our field is not 2, which we'll assume from now on, that's the equivalent structures. So you can really think of this as quadratic forms over the field F. That's the Grothendieck-Witt ring. And the Witt ring you get by just modding out the Grothendieck-Witt ring by hyperbolic forms. You have a vector space V, you have its dual space. There's a canonical bilinear form on V plus V dual, just by the pairing. In terms of matrices, that's just the matrix 0, 1, 1, 0. That's symmetric matrices, where the 1 is the identity matrix. And so you mod out by that, that ideal. In other words, this is not really a ring, but of course it's a module for the Grothendieck-Witt ring of F with values in F. You have a tensor product acting there, and the hyperbolic form is living in the Grothendieck-Witt ring of F with values in F, in other words, the trivial L, and you mod out by the action, by the hyperbolic forms. It's an amusing thing that if you multiply an arbitrary quadratic form by a hyperbolic form, it's just a multiple of the hyperbolic form, the multiple being the rank of the quadratic form times the hyperbolic form. So the ideal is the same as the subgroup. In any case, that's the Witt ring, or Witt groups. So there are two very simple maps. You can send a vector space to its rank, and that gives you our dimension that extends to the rank homomorphism. It's a ring homomorphism from the Grothendieck-Witt ring of F to Z. And when you mod out by the hyperbolic form, that's a rank 2 form, so it gives you a reduced rank to Z mod 2. And the two constructions are related in a very simple way. So you have a Cartesian diagram which just looks like this. You have the Grothendieck-Witt ring of F. It reduces down, we call it pi, to the Witt ring of F. Then you have the rank map to Z. You have the reduction, if you like, to Z mod 2. And you have the reduced rank here. And this is a Cartesian diagram. In other words, an element in the Grothendieck-Witt ring of F is just an element in the Witt ring and an integer such that the reduced rank of the Witt element agrees with the integer mod 2. So if you want to get an invariant here, it's enough to get an invariant here and an invariant here that agree there, which is what we'll be doing. All right. So here's the cohomology theory we're interested in. Remember, the Chow ring was represented by an Eilenberg-MacLane spectrum on Milnor K-theory. There's a similar homotopy module, which is just repeat the Witt. So maybe I should say, I forgot about this, some properties. Sorry. So if the field is quadratically closed, for example, an algebraically closed field, the rank homomorphism from the Grothendieck-Witt ring, and that's not an F, of course, that's a Z, is an isomorphism. The signature map, if anytime you have an order on the field, you get associated signature map, and that will be an isomorphism if the field F is real closed. These constructions extend to sheaves. For example, the Grothendieck-Witt ring F with coefficients in L extends, as I mentioned, to a sheaf of Witt groups with values in an invertible sheaf. It also, if you twist by the square of an invertible sheaf, it doesn't change anything. Why is that? Because you can always absorb a square into a quadratic form by change of variables. You have a sheaf of commutative rings for the Grothendieck-Witt ring, the twisted ones, and of course that should be a, sorry, it's just the GW of L on the right there. Can you see? No, it doesn't do anything. Oh, sorry. This doesn't do anything. Does it? Let's see. Kind of, you can't see anything. Okay, so it just, the notation, there's a typo there. It's just the DWX of L is a sheaf of GWX modules. And the whole thing works also for sheaves of Witt rings and twisted Witt groups. Yeah. Yes, exactly. This is GW of F to Z. It's a typo. Thank you. Right. So now that we have these things, the relation with the Motivic homotopy category is you have this Eilenberg-MacLane object. And when you take the Eilenberg-MacLane object in bi degree AB on X and twist by, let's say, a virtual vector bundle of virtual rank 0. So you just take your arbitrary, say, perfect complex, subtract off the rank part, give something of rank 0. And that's exactly the cohomology of X in this sheaf of Witt groups twisted by the determinant of your perfect complex. So it becomes quite concrete. It's just usual cohomology of this sheaf. And the same thing, the Borel-Moore homology, well, what is this? I mean, that's just what it turns out to be in terms of the Motivic homotopy theory. But it's very much like the Chow groups. You have a complex. In the case of the Chow groups, remember, we have this divisor map from functions on things of dimension m+1 to the integers on things of dimension n. In the case of the Witt sheaf, the part in the middle, this x and z of n, w of k of x, and then you have these funny twists. Well, what are these? What's this new? This, yes, this new is the normal bundle of, you take some dimension n subvariety. At the generic point, it's smooth. It has a normal bundle in X. So that's this new X. That's the determinant of the normal bundle is this new X. And then you also, so for reasons of Poincare duality, you also have to twist by the relative canonical sheaf of X over Y if we're taking the Borel-Moore homology of Z over Y. And then we have the twist by our line bundle L. We have to include that in the information. But forgetting the twists, a element in Hn Borel-Moore of Z over Y is just gotten by an n-dimensional, let's see, is that, Yeah. Yes, n-dimensional subvariety, some of with coefficients in the Witt groups of the residue field. Then you mod out by something which looks kind of like a divisor map from things of dimension n+1, and you have a further divisor map to things of dimension n-1, which has to be 0 in order to get a cycle in this complex. So it's a somehow fancy version of the Chow groups of dimension n things. You have something corresponding to the divisor map. The coefficients, instead of being in the integers, are in the Witt groups. And you have an additional condition of a co-boundary. It has to be 0. So it's not too far from the Chow groups. Again, we have the Poincare duality in the general setting translates into this Poincare duality statement. Again, you see you get a twist by the relative canonical sheaf, and the twist by L gets changed to the twist by L dual, which actually you don't really see because L and L dual just differ by the square of L. Now, what does this have to do with anything? So I mentioned the homotopy, the quadratic theory is supposed to tell us about things over C and things over R. The Witt sheaf is very close to the singular cohomology of the R points of a variety. If you take the Witt sheaf cohomology of X and you invert 2, you just get the singular cohomology of the real points of X with coefficients Z with 2 inverted. That's given by the signature. That's a theorem of Jacobson. The interesting arithmetic information like discriminant, Hasse-Witt invariant, that type of thing is killed by inverting 2. You don't see that. But sort of this integer information given by the signature is just giving you something about the real points of X. So that's why it's useful to give this Witt sheaf cohomology then tells you something about the enumerative geometry of problems over the reals. Now, you have a degree map from the dimension 0 Borel-Moore homology of X over K without any twists. Just the push-forward map for the general theory maps to the dimension 0 Borel-Moore homology of spec K, but that's just the Witt groups of K. So you have a degree map landing not in the integers, but into the Witt groups of K. And that's where the source of all the quadratic enumerative invariants. Okay, so let me just say a little bit about the history of quadratic intersection theory in general. It began with the introduction of these Chow-Witt groups. This was by Barge and Morel. Again, the notation suggests it's like the Chow groups, but you have the additional information of a twist by a line bundle. I didn't say this before, but these twists by line bundles, if you remember this connection with the real cohomology, for a manifold over the reals, you have the notion of orientation. It's very important if you want to have a proper map of real manifolds. You get a push-forward map in cohomology, but it has to be an oriented map. You need a relative orientation. And that's exactly the role of these twists by the line bundles. They play the role of an orientation. So these Chow-Witt groups, again, they're an Eilenberg-MacLane spectrum construction for a homotopy module of Milnor-Witt K theory. The Milnor-Witt K theory is something which lives over the Milnor K theory in one direction. It maps onto that, but it also maps on to the Witt theory. So you form this, it's sort of the Chow-Witt groups map, they refine the Chow groups, and they also map to the Witt sheaf cohomology. The map to the Chow groups is similar to the map of the Grothendieck-Witt ring to the integers by the rank. You're taking a quadratic form, think of, again, something in the Chow-Witt group is like a quadratic form on a subvariety. You're replacing that with an integer on the subvariety by the rank map, or you can replace it with something in the Witt ring on the subvariety by just taking the quotient map from the Grothendieck-Witt ring to the Witt ring. That's exactly this construction here in these diagrams, and it works for the cohomology and for the Borel-Moore homology. The whole idea now is you have some enumerative problem, you solve it by methods of modern algebraic geometry, taking an Euler class or intersection. You eventually get down to something on a projective variety of dimension 0, and then the count is gotten by taking the degree map. So I hope I've shown you that all these structures are available for, in this Motivic setting, so in particular for the Chow-Witt groups, and also for the Witt-Schief cohomology. So the plan is you have some enumerative problem. Let's say you know how to solve it in the Chow groups to get an integer invariant. You want to get the Grothendieck-Witt invariant by doing work in the Chow-Witt groups. That's a little complicated because the Chow-Witt groups have information from Chow theory, which is like the complex embedding, and the Witt theory, which tells you about the real embedding. And they're somewhat different in terms of their calculus. So it's better to separate the two into two different problems. Calculate the Chow group part, calculate the Witt-Schief part, and then that gives you your two invariants, and they match up mod 2 by the ranks, and that gives you your Grothendieck-Witt quadratic invariant. That's the plan. Okay, so I hope that's clear. And I think that's kind of what I just said was here. So the problem is, okay, step 1. You do what people did before with the geometry, and you just do it using this Witt-Schief cohomology instead of the Chow groups. You end up with some class on your projective variety in Borel-Moore homology in dimension 0. But the fly in the ointment is there'll often be a twist involved. In order to get the push forward, you have to get rid of the twist, which means you have to orient your problem. Orienting your problem means you have to choose an isomorphism of your twist, which comes from the problem, to the square of some line bundle. So that gives you an isomorphism on the Borel-Moore homology. But then you can absorb the square into the Witt-Schief because you can just change the variables, allows you to absorb squares. Now you're in the oriented situation and you can take the push forward. Note that this depends on the choice of this row. You can always change your row by a minus sign, for example. That's why often counts of enumerative problems in the reals are up to a plus or minus. It depends on the choice. In any case, that gives you your quadratic count. Then you have the problem of how do I compute it and what does it mean? Okay, any questions so far? I should have maybe asked before, but I'm asking now. Questions? Okay, good. So let me give a simple example. See how I'm doing for time. I think I have a good amount of time here. Okay, this is a rather simple problem with a concrete answer. You take a smooth hypersurface in Pn of degree d is 2n minus 3. And essentially, the lines on x, what does it have to do with this sim d of this E2n plus 1 dual? So you take the Grassmannian of two planes in n plus 1 space. That's the same as the Grassmannian of lines in your projective space. You're counting lines. And it has the canonical rank 2 tautological subbundle. Now, if you have your x is given by a homogeneous form of degree d, you restrict to each of these two planes, you get a polynomial of degree d on the two plane. In other words, a section of sim d of the dual of that bundle. And of course, if you have a section of a bundle, and if it vanishes, this d is chosen so that the rank of this bundle is the same as the dimension of the Grassmannian. So you would expect a general section to vanish at finitely many points. You count the points with multiplicity, that gives you the top Chern class. So you'd expect that this count, this is the expected number, is just the degree of this top Chern class of this sim d of this dual tautological bundle. Good. So there are lots of methods developed for counting this thing. You know what the Chern roots of this bundle are, and you can use that to write down the Chern class, this top Chern class of sim d in terms of the two Chern classes, the C1 and the C2 of this bundle. And then the Schubert calculus tells you how to calculate its degree. It's a fairly standard thing. It's a lot of fun to do with the Young diagrams and that type of thing. And when you do it, first of all, you get the classic 27 lines on a cubic surface, 2,875 lines on a quintic, et cetera, et cetera. And there's the general formula. it's a little complicated. You see the number of terms in the formula grows in terms of the dimension or the degree, either one. This d double factorial is, d is going to be an odd number because it's 2n minus 3. It's d minus 2 down to 3 times 1. Okay, so this is going to show up again. It's a rather complicated formula. So what about the quadratic version? You just do the same thing. You take the Euler class for the Chow-Witt theory or the Euler class for the Witt theory. You get something in the Chow-Witt group, Borel-Moore homology in dimension 0, or the Witt-Schief Borel-Moore homology in dimension 0. But the twist is, that's what the twist is. It's the determinant twisted by the structure, by the canonical sheaf. Fortunately, it's easy to compute what that is, and it's always a square. So you can always absorb it, and that gives you your orientation, and you get a degree. And so that gives you a definition of the Grothendieck-Witt degree and the Witt degree. In fact, you can compute this, and it has a very simple formula. There are various stages of the computation listed: Cass-Wickelgren, Sabrina Pauli, myself, and the final answer given by Bachmann and Wickelgren. It's just this d double factorial in the Witt ring. That's the Witt ring count. It's very simple. And this was also seen by many people before: Okonek Telemann, Finashin, Karlamov. This signature, which is, I mean, the signature is just the number. When you count things over the reals, you're counting things with a sign, plus or minus, possibly with multiplicities. If you just counted the multiplicity, the absolute value, the signed count would be a lower bound for the actual count, if you like. So this gives you a lower bound for the number of real lines, assuming it's a finite number. There are, of course, examples where you have, in the case of cubic surfaces, you always have the finite number 27. Once the dimension gets higher, you sometimes get things with infinite families. So let's just ignore that. So the correlate, now you put these two things together. We know that the real count, the count for the Chow groups over C agrees with the count for the Witt ring mod 2, and you, right? And so this gives you a formula for the Grothendieck-Witt answer. I mean, for what it's worth. This H is the hyperbolic form. And also, you can, just using the formulas we have, you get this amusing estimate that when you look at the ratio of the logs as the dimension or the degree goes to infinity, it goes to 2. In other words, you have roughly the square of the number of complex lines as the lower bound for the real lines. This square turns up quite a lot. So another problem, let's see, how are we doing? Yeah, still doing good. So another somewhat less classical problem. So Berger mentioned Fano varieties. The Fano varieties of dimension 2 are called Del Pezzo surfaces. So you take a Del Pezzo surface, for example, P2, P1 cross P1, various other examples. You take an effective divisor, and this gives you the question is, if you take the complete linear system of the effective divisor, how many, and you fix the right number of points, so you get a finite number, how many rational curves in the linear system pass through those points? And the number of points you choose is you take d times the embedding, the ample bundle minus k, that's the degree of d, minus 1. That's the right number of points. You fix minus k times d minus 1 points. You look at curves in the linear system, finite many, if the points are in general position, should be rational, how many? And Kontsevich, there was a lot of progress into this. There's difficult progress, I think, in the early days. It got up to maybe degree 7 in P2 with Kleiman and Caparasso, I think. Got some answers there, but it became quite difficult until Kontsevich came up with a different approach, developed this moduli space of stable maps, building on the Deligne-Mumford moduli space of curves, of stable curves. He had the moduli space of stable n-pointed genus 0 maps to your surface. So C is a genus 0 curve, possibly singular with nodes. P1 for Pn is a choice of n smooth points on the curve. F is a map of the curve to your surface. Now there's an evaluation map. If you have your map, you can take the value of f at the endpoints. That gives you endpoints in S. That gives you the evaluation map from the moduli stack to S to the n. And what you're doing is, if you fix, on the other hand, you fix endpoints in S, n is this number that we're looking at, minus kd minus 1. You fix endpoints, you'd expect to have finitely many such curves passing through those points. It's just the inverse image of the evaluation map gives you all the curves passing through those points that are rational. And so the expected number is just the degree of this evaluation map. So the classic examples, you take S to be P2, you take, of course, D is just D, a positive number D times a line, and there's a beautiful recursive formula for calculating these things. In general, in fact, there's a recursive formula, and this is what you get. Of course, 2 points. How many lines are there through 2 points? Anybody know? All right, 5 points, conic through 5 points, there's 1. If you take degree 3 curves, cubic curves or elliptic curves through 8 points, 12 of them will be rational, then the numbers grow quite spectacularly as you increase the degree. Okay, so with Jesse Cass and Jake Solomon and Kirsten Wickelgren, we gave a quadratic version of this theory. We do exactly the same thing. That's the principle. You just follow your nose with what other people did, and you want to calculate the quadratic degree of this evaluation map. What do you need? You need an orientation in order to do that. So what we showed is by removing a codimension 2 subset of our target space, S to the n, the inverse image will be this M0n bar is a stack. It's not a scheme in general. But by removing a codimension 2 subset of the target, you can make it into a smooth scheme. The evaluation map is then a finite map, and it's also oriented. So we're very proud of this orientation. It uses the geometry of the evaluation map. You want to know the ramification locus of the evaluation map, and you want to write that divisor as linearly equivalent to the square of some other divisor. That comes from looking at the universal curve, mapping to your surface, and looking at the points that come together, then mapping that subscheme back down to the moduli space and looking at its discriminant locus. That turns out to give you the square. Anyway, that was fun. And so we have our quadratic count. That's what it is. You just take the push forward of the unit section. So how does that work? You're on this open subscheme. Then you have your square of your line bundle, which is equivalent to the relative canonical sheaf. So you can absorb a square. You make it isomorphic to the relative canonical sheaf. You use Poincare duality to go into Borel-Moore homology. You take the push forward, Poincare duality again. But now here's something amusing. You're just in the H0 of the Grothendieck-Witt sheaf on this open subscheme. But you've only removed a codimension 2 subset, and you have a nice purity result due to Panin and other people, which says that a section of the Grothendieck-Witt sheaf over a smooth scheme minus a codimension 2 subset always extends canonically to a section over the whole scheme. So you actually get a global section of the Grothendieck-Witt sheaf. In many cases, for example, if S is P2, the global, you can compute what this global sections are, and it's just GW of K. So you actually have a constant which tells you your answer. That's not always the case, but it is in that case and many other cases. So that's our quadratic curve count. Okay, so it doesn't tell us how to compute it, but fortunately, tropical methods, which are very powerful methods for computing these curve counts, have been refined also quadratically by Andres Yaramil Fuentes and Sabrina Pauly, and they use these tropical methods to actually give computations. So here's one example. You also don't have to use n points on your surface. That would be, if you're over a field k, that would be n k points on your surface. You can also use a 0 cycle of degree n, where the residue fields are in different fields, just as long as the sum of the residue fields adds up to this number n. So the quadratic count for rational cubic curves passing through R closed points in P2, where the sum of the degrees is 8, is given by this formula. So this bracket -1 or bracket A is the quadratic form x goes to ax squared. So this 1 plus minus 1 is just the hyperbolic form. Then you have a trace form. If you have a finite field extension, you can look at the sort of multiplication table in a basis. That's a symmetric matrix, and you take the trace of the terms in that matrix. That gives you a symmetric matrix over your original field, and that's the trace form for that field. So that's exactly the formula you get. And you can also relate, once you have a formula for 1s, which is a simple s, you make it a little more complicated by putting it in a family that acquires an ordinary double point. In terms of the real locus, that's like a surgery on the real points. And Erwan Brugalet and Kirsten Fickelgren have written down a wall crossing formula, so it enables even more computations. And similarly, for the change of residue fields, Andres and Sabrina have a wall crossing formula there. So there are a lot of computations of these things, even though a general formula is not available. So let me finish up with another method, torus localization. This is a very powerful method for computing enumerative invariance in the Chow group. The basic idea is you have some enumerative problem, you get a class in the dimension 0 Chow group of some projective variety z, the degree map gives you your invariant. How do you compute it? One way is to impose a torus action on the whole problem. So make it equivariant. You get all the invariants now live in an equivariant version of the Chow groups developed by Totaro, Edidine, Graham. You get an equivariant class, but you have you have an equivariant degree landing in actually the Chow 0 of B of the torus, but that also turns out to be Z. The entire Chow ring of B of the torus, the classifying space of the torus, is a polynomial ring. The degree of the variables are 1, so if you have something in degree 0, it's just an integer, and that's the integer you want. Now, then how do you compute it? You have this very effective method of the Bott residue theorem, which tells you you can compute the answer, the equivariant answer, by localizing to the fixed points. That's the method. So here it is, the equivariant Chow groups of some x after you invert some polynomial in these Chern classes for the classifying space is the same as the equivariant Chow groups of the fixed point. But since the fixed point has a trivial action, this is just the Chow groups, usual Chow groups of the fixed point locus, tensor the Chow groups of BT. And if the fixed point locus is just a finite set of points, which is what you hope to get, then it becomes a problem in representation theory. And the answer is given, what the actual computation is given by the Bott residue theorem. It tells you exactly how to get the thing in the equivariant Chow groups of the fixed point, which maps to your given class in the variety. So this is really makes the whole problem into a problem in representation theory. Now, there's a fancy version of this which uses, instead of, say, Euler classes of vector bundles, uses so-called virtual fundamental classes, and this is really central to modern Gromov-Witten theory and Donaldson-Thomas theory. Maybe I'll just not say too much about this. It's a way, if you have perfect obstruction theory, some homological data on your variety, you get out of it a class which is telling you if your variety has big dimension, but you still want to count something of 0 dimension, if you view the variety as coming from some obstruction problem, you can often get a 0-dimensional class out of that, or a smaller dimension. That's this virtual class. And there's also a localization theorem for the virtual classes given by Graeber and Pandarapande. Okay. So this is a quick explanation, since I'm almost out of time, of how you get the equivariant Chow groups. If you're familiar with the equivariant theory in topology, you want to get a space which is contractible on which the group acts freely. You can't do that in algebraic geometry, but you can approximate it. One way to approximate it for a subgroup of GLN is you take n by n plus m matrices of rank n and let the m go to infinity, where the GLN and then your group is acting on the left on the matrices. So that turns out to give you a reasonable approximation, and then you can use that to define the equivariant theory. Okay. So what about the quadratic theory? Well, there's a problem that when you try and do torus localization for Vitchev cohomology, it fails completely because you can compute the Vitchev cohomology of Bt is actually 0 in positive degrees. There's a general fact that the Euler class of an odd rank bundle in Vitchev cohomology vanishes. So all these line bundles, which are giving you the generators for the Vitchev cohomology of Bt, their first Chern class all vanish. So you don't get anything, and you get a polynomial of degree n that you want to invert while it's a 0 polynomial, and you get the theorem that 0 equals 0 after inverting that, which is true but useless. There's a solution to that, which is you replace that's just GM, the one-dimensional case. You replace GM, you view GM as the diagonal torus inside of SL2, and you replace it with a slight non-commutative extension. You just take the normalizer of that torus. And it turns out the Vitchev cohomology of Bn looks very much like the Chow groups of BGM. So it's generated over the Witt ring of K by one generator, now in degree 2. Remember the analog with the real points. If you take BGM and take its real points, it's CP infinity, and that has a generator in degree 2. So that's the WK adjoint E. Then there's one extra element in degree 0, which disappears after dividing by E, which you're going to localize with respect to E anyway, so it doesn't really bother us too much. So that's the replacement. And you have the analog of the localization theorem, the Graham added in the Tia-Bott localization theorem for Vitchev cohomology using the normalizer instead of the torus, an analog of the Bott residue theorem, and you also have an analog of the Graeber-Ponderapande localization. I should say that these methods of constructing the virtual fundamental class from a perfect obstruction theory go through in complete generality for any motivic theory that we discussed right at the beginning. So there's no problem with that. And the localization theorem works very well, at least for the Vitchev cohomology. So my former PhD student, Alessandro D'Angelo, extended this to a wide class of theories. It's not just for Vitchev cohomology. So let's see, I have only a few minutes. This is this famous example of Ellingsrud and Stroma. They use torus localization to compute the number of twisted cubics on a degree D hypersurface for, again, when you get the expected number would be finite. And the classic case they got, which came from a problem out of mirror symmetry, was to compute this number, not using physics, but using algebraic geometry. I think the first time they tried it, they didn't get this answer, and it was, as C.C. Ting said, then it was very exciting because it didn't agree with the theory, but in the end, it agreed with the theory. And so with Sabrina Pauli, we have a similar computation. We don't quite get the answer in the Grothendieck-Witt ring because we use localization. It inverts things, then we recover a bit by spreading things out over the integers with 6 inverted, and we get an answer modulo these 3 quadratic forms of rank 0. But more or less a good answer in the Grothendieck-Witt ring. Here's a table for your amusement. Ponderapande, Solomon, and Walscher compute this using holomorphic disk methods. And in the cases where we both have comparable computation, they get twice our answer because the P1 has 2 disks. It has the upper half plane and the lower half plane. So you should get twice the answer if you use the disk method. And yeah, we also get things for complete intersections of certain degree. And again, we have now, you get an algorithm, the torus localization and localization gives you an algorithm. It doesn't give you a formula, so we can't really write down the complete answer as a formula, but we suspect that you also have this ratio of the logs tends to 2. Let me conclude. I think I have another minute and 21 seconds. So Donaldson-Thomas invariance is another example where you compute the degree of a virtual class. This was done by Malik, Nekrasov, Okonkov, and Ponderapande for the case of a smooth projective toric threefold. They look at the Hilbert scheme of 0-dimensional degree n closed subschemes There's a Donaldson-Thomas perfect obstruction theory. It has a virtual fundamental class. You have its degree. That's this invariant In of x. You write down the generating series. And they showed that in the toric case, you get this beautiful formula for the generating series in terms of this McMahon function counting plane partitions. So this was the toric case, and this was extended to Calabi-Yau threefolds by Baron von Tecke, and then Jun Li, and using a different argument, myself and Pandey extended this for arbitrary threefolds. So again, all the framework works in the quadratic case. You need an orientation, and I could show that the thing you need to get an orientation on the Donaldson-Thomas perfect obstruction theory for the Hilbert scheme is exactly a spin structure on the target threefold. Time's up. So we'll finish with this. You get an orientation, you get a degree, you get a generating function, and we have two computations due to my student Anneloes Viergever. She looked at the case of P3 and could show that all the odd invariants vanish, and she computed the first three even invariants and got a formula, at least for those invariants, that agrees in form with the MNOP formula. And then together, we looked at the case of P1 cubed and actually got the full formula. Finally, we conjecture that something like this works in general, whatever. Here's some remarks, but let me end with the last question. What does this all mean? Even in the case where we have an interpretation in terms of the complex numbers and the real numbers, okay, then we still don't have a good idea of what the other quadratic invariants mean. Discriminant, Hasse-Witt invariant. What is that telling us about the geometry of the situation? And in this case, we don't even, I don't really know what Donaldson-Thomas invariants over C mean. Probably some of you have a better idea. But what does it mean over R? What are these signatures of these quadratic Donaldson-Thomas invariants telling us at all? So it's a question for you to work on. Thanks very much.
So thank you for your wonderful talks. So any questions? Oh, okay.
Yeah. Oh, Maury, yes. Yes, please. Sure. Yes.
Does the formula mean that on a general cubic surface there are genuinely 27 different lines?
Yes, in the case of cubic surface, I think that's a known result.
Yes,
that it really is 27 different lines over
But,
C. Over C.
Yeah,
they don't come together. There are no multiplicities. I think
but for the general, if you say
no, for any smooth, I think the theorem is that for any smooth cubic over C.
No. For smooth cubic, that's okay.
Oh,
I know.
we
but
don't,
for very general setup, if you say the formula says there are such and such a number of lines or objects,
yes.
What does exactly mean? For the generic case, do you mean that there are exactly that number of objects?
Yes, that's true, but in the case of cubic surfaces, it means for every smooth cubic surface, there are 27 separate lines over.
Yeah, but for instance, for Fano variety.
Then it's very different because sometimes they're infinitely, even if you fix the degree, so the expected number is fine. I think for a quintic, if you take maybe a Fermat quintic, I think there, is that right, Yves? Do you know?
That's okay.
I think in that case, you'd expect to get a finite number of lines, but there are cases where you have infinite families even. So, but for the general one, yes. Even then, I guess it's probably, yeah, on the general one. Yeah. But if you allow the dimension to go up, I'm not even sure what the story is for the general one, to be honest.
For instance, if the formula gives a positive number,
yeah,
it means there is a line.
Yes, absolutely, yes. Yes.
Okay.
And similarly, in the case of the real formula, it means there is a real line. You get a lower bound. This d double factorial is a lower bound, but it really means there is. But that's not so hard, because the fact that there is a line is not so hard because over the reals, because it comes from some odd degree extension.
Yeah, but
So then you have a real point.
In general, in the enumerative geometry, you give a formula for some objects.
Yes.
And if the number is positive.
Yeah. Yeah, you don't necessarily know anything. That's true. Yeah.
Okay.
Yeah. Yeah, Eve, you had a question?
So you after giving this quadratic principle of enumerative geometry, you specialize your formulas to the field K is C or R.
Yes.
Would it give something interesting for K, a p-adic field using Hilbert symbols?
A
p-adic field.
Yeah. Interesting. I mean, you get okay, so many of the cases, the quadratic answer just involves sums of ones and minus ones. Maybe not so interesting. Usually what happens when it doesn't, it means that the problem is degenerating at that prime. If you get quadratic form, which is no longer, involves like a p in the quadratic form, then often, it means that the problem that you looked at, the objects become singular, something degenerates at p. But this goes back to my question. Over a p-adic field, then you have the discriminant and the Hasse-Witt invariant. What does that tell you? I don't know. I'd love to know. I'd love to know more specifically in a particular enumerative problem, what does that tell you? You have one quadratic computation, which I didn't mention. It is really the first one that we did. It goes back to work of Marc Levine, and then I extended it, and various other people extended it. You have an A1 Euler characteristic of a smooth variety. It's a smooth projective variety. And it also, you can write down there are many ways of techniques of computing it. For hypersurfaces, it's a purely algebraic formula. For an arbitrary smooth projective variety, you can compute it in terms of the cup product on the Hodge cohomology and the canonical trace decay. That gives you a quadratic form. That's what it is. So then there was work of Takeshi Saito, which tells you about the discriminant of that form in terms of the discriminant of the Galois representation. If you have a Galois representation, you have the Galois representation on the étale cohomology of the smooth projective variety. In the middle dimension, it has an orthogonal structure due to the Poincare duality, and it gives you an orthogonal representation, which then gives you a mod 2 character, which corresponds to a quadratic extension of your base field. You can take the discriminant, and that discriminant is up to some minus ones, which come from the Betti numbers or the Hodge numbers, is exactly this de Rham discriminant. So he showed that. So that's what either of those mean. Maybe you can tell me what the Galois theory one means, but that's a relation between this A1 Euler characteristic, its discriminant, and something coming from Galois representation theory. And I think he also has some formulas for the Hasse-Witt invariant, which are quite complicated. So that's some interpretation. For meaning, I don't know. I'm not a philosopher, so I'm not going to tell you what does mean. But yeah, those are some examples that I know about. For what? Oh, for the Donald? No, we don't. For that case, as I understand it, you need to take some quadratic extension to split some. You have some linear space of linear spaces inside some quadrics, and you need to split that. Probably that would destroy. Taking quadratic extensions destroys a lot of quadratic information, right? It destroys the square root. Right? You have a square root of something, you lose that form. So modulo that, you may get an interesting answer. I don't know. But it's certainly something worth looking at. Thanks for the question.
Since we only have a short break, so maybe if you have further questions, maybe after the talk. Okay, so let's thank Professor Levine again.